Welcome back to the video lecture series for Introduction to Data Programming using Scala. This video, while we're still on the topic of linked lists, we're taking kind of a little detour, and we're going to pull back to the ADT of stacks and queues. In particular for this video, we're going to talk about stacks. Remember, one of the key things about an ADT is the abstract part. It says that we have a set of operations, but it doesn't tell us how those things are done. It doesn't tell us, in the case of stacks, queues, linked lists, how it's actually going to store the data. And so you can make multiple ways of doing that. When we talked about stacks previously, we wrote an array stack. So we had our trait for the stack here. It has its four methods, and it has to do it has to have the behavior of being LIFO. So the last thing that we push in is the first thing that we pop out. And we did this very nicely using an array. Well, now I want to do this using a linked list instead. Okay? And so the question is, well, how can we go about doing that? So I want to create a new class in here. We will call our class a list stack. We have an array stack. Okay. And the question, one of the first questions we have to ask ourselves is what type of list do we need to use? I'm making this to a mutable stack. We wrote mutable lists using both singly linked and doubly linked lists. And the question is, which should we go with here? And that question can be answered really by looking at what our needs are. So the doubly linked list with a sentinel was really great for the for when we were doing code that needed to have random access or needed to be able to insert things. But that's not what we're doing here. So it's not clear that we need all of these extra pointers going around. We don't really need the sentinel because in the case of the stack, we have a much simpler requirement. We're going to add things at the top, wherever that is, and remove things at the top. And so the only question for a singly linked list is which side should be the top, the head or the tail? Well, so I need an end that I can both add to and remove from. We've seen that if we keep track of the head and the tail, I can add efficiently to the head and I can add efficiently to the tail. We were able to do a very efficient prepend and a very efficient append on our singly linked list. The efficient append was only allowed by the fact that we kept track of our tail. What about removing though? Well, the thing about removing is that in order to remove the tail, we have to know not the tail but the thing in front of it. And so it turns out that you can't efficiently remove the tail from a singly linked list. I can efficiently remove the tail from a doubly linked list, but not from a singly linked list. And so for that reason, really the side that I care about is the head. And so I'm going to make the head of my list be the top of my stack. We could have it so our stack actually just used the code for the linked list that we've written previously. But especially for educational purposes, you're just learning how to write linked lists. I think it's advantageous for you to see the act of writing the linked list logic again, and then specifically see how it goes inside of our stack. So if we come in here and we'll copy out these methods, we'll make our list stack, give it the type argument, and say it extends my stack of A. And we put in these methods. Okay, and then the question is, well, how do we implement these? Well, we just said we're going to write a linked list, so I'm going to go ahead and make my node class because I know I'm going to need one. It's a singly linked list, so it has a data element A and a next reference to the next node. Also, I need a top. It is our node. It is exactly the same thing that a head was in our full singly linked list. It's going to point to the same thing, the first element. I don't need to keep the other end because it turns out in the case of a single and of a stack, I never interact with the other end. Okay, so let's start off by writing the easy methods here. Is empty. Well, top is null. If top is null, the thing is empty. Peek. What would we get if we popped off the next thing? That would be top.data. What happens when we pop? Data member, oops. Let's see. Now this is interesting. I'm going to follow my standard rule of we make it vals unless we need to make them turn them into vars, and we'll see how far that goes. So what about top? Well, top, the pop method needs to pull off the first element and give us back that value. So it needs to give us back data.top, but it also needs to move the pointer so that it's no longer on top. So I'm going to create a temporary variable that's equal to top.data. Then I set top to point to the next thing, and I return that value. And oh, I'm missing an equal sign. Wow, those are some interesting errors for missing an equal sign. Okay, and last we have push. Well, push is simply top equals new node of the data that I'm pushing, comma, the current top. So this builds a new node, storing that data that has top as its next pointer, and then it sets top to be that new pointer. And there we go. We have a list-based stack. It would be good to test this. Because we're following the exact same interface, all of our code from our test of an array stack, turns out, whoops, let's go over here, all copy, will translate over. So if I come in here and I make a new class for test list stack, what do I have to do? Well, I'm going to change the name, so it's not called an array stack, it's called a list stack. And the stack is now going to use a list stack, and I'll change my import to use a list stack, and bingo, there we go. Because it follows the same interface, those are the only changes that I needed to make, and I should be able to run this as a unit test. And I have 4 tests in here, and they all pass green bar, so we're happy. You'll note that the list stack is actually pretty simple. In fact, it's even a little bit simpler than the array stack for one reason, and that is the fact that we don't need this code right here. This was the code that made the array larger. I don't need that here because in this case I'm always making a new node. So your trade-off is this has to create new nodes, potentially lots of them if you have a lot, but it never has these occasional large allocations of memory and copying over. So it's just an alternate implementation that has, depending upon what your application is, you could go in and figure out which one of these is better for your particular application. In our case, it's another illustration of how we can use the linked list structure to implement an ADT that we had previously implemented using an array to store the data. Okay, so that's it for this video. We wrote the list-based stack, we ran it through the test that we had written for our array stack, and it passed. So we'll come back next time and we'll write a list-based queue.